All right, so today we're going to take a look at exponential growth. So we're going to look at a couple different examples of what exponential growth is and how it works. So we've also talked about the story, One Grain of Rice. So if you're interested in a mathematical story that kind of has to do with exponential growth, you can check that out. This is just for the video. So we're going to take a look at a bacteria culture. The number of cells in this bacteria culture is going to triple in number every day. On the day we begin observations, the bacteria has a population of 100 cells, and we're going to make a table to show the population over the next 5 days. Okay, so that will be the initial observation. No time has passed. It's day 0. And we'll take a look at what's happening over the next 5 days. So remember, your bacteria, your number of cells in this bacteria culture is tripling every day. So in the initial observation, we have 100 cells. After 1 day, how many cells are we going to have if this is tripling?
300.
Okay, we're going to have 300. So essentially, you're telling me we're multiplying by 3 if we're tripling? Yeah? Okay, day 2? 900. Day 3? 2700. Multiply by 3, yeah. Okay, day 4?
81.
Yep. 8100. And day 5? Should get 24,300. Okay, just multiplying each time by 3. Okay, so we can already see after 5 days, this has grown very quickly. Just like in our 1 grain of rice story, by the end of 30 days, Randy has over 1 billion grains of rice, right? So the idea of exponential growth is that something could start small, but it's going to get really big really quickly. So if you guys look here, I've just taken a little kind of section of that, and I just want to show you about the finite differences. So just to recap, you guys did this a lot in grade 9 and 10 to decide if functions were linear or quadratic. And basically what it is you take the y values here, and you do bottom minus top. So you're doing like 300 minus 100, and then 900 minus 300. 2700 minus 900, and so on. And then for the second differences, you take these values and you do bottom minus top. So we get 600 minus 200, and so on. Now in exponential functions, you will notice that the first and second differences are also exponential. So what do you guys notice about getting from 200 to 600, 600 to 1800, 1800 to 5400? These are also all tripling, yeah. So our finite differences are tripling, so the first differences. How about the second differences? Yeah, these are also tripling. So I can tell if a function is exponential by checking the finite differences, and if they have a constant multiple that is occurring between each of them, like times 3, times a half, times 2, anything like that, then we can say that function is exponential. So it won't necessarily always be times 3, but any multiple that is consistent, that means that your function is what we call exponential. Okay, so we're going to plot these. I'm not going to plot day 5 because that gets really high and that's kind of off our graph here. But we're going to plot these points, 0, 100, it's about down here somewhere. 1, 300, 2, 900, 3, 2700, and 4, 8100. Okay, so here's our graph. All right, so this is the function that is representing where the population starts. So you'll notice on the y-axis, our population has a starting value of 100. And then Exponential growth, we said it gets really big really quickly. So it starts off just kind of like with a bit of a curve, and then it shoots up because those values are tripling, right? So every single time you triple, it's getting larger and larger and larger and larger, okay? So this is kind of what your graphs of exponential growth are going to look like. All right, so here's the question. Can we create an equation to represent the growth of this bacteria? So I have some value. Let's just say I'll have a future value y. Okay, y here is representing population. And here x is representing time in days. So I have some population y at a certain time. My starting population is 100, so we're going to be starting with 100. And then what did we say that we were doing here to get more y values?
Multiplying by 3 each time.
Okay, so we're multiplying it by 3 each time. So to get from the first one to the second one, I'm multiplying by 3 once. But to get from the first one to the third one, I'm multiplying by 3 twice, right? So I'm multiplying 3 times 3. What's another way to write 3 times 3? Well, or 3 squared, right? And then to get from the first one to the third one, I'm doing 3 times 3 times 3. What's another way to write that?
But why would you write it?
3 cubed. Well, we need to create an equation, right, which represents any time. So here, I'm going to multiply by 3 to the exponent x. And that's going to give me at a certain day. So if I wanted to find the population at day 27, I should be able to enter that in for x, and that will give me the population at any time. Okay, so we're going to unpack this a little bit more. But this is basically an equation to represent what we were just talking about. All right, so here's the general equation that we're going to use for exponential growth. Tomorrow we're going to do exponential decay. So A here, this value is kind of like our 100 in this example, and that would be the initial starting value. So how much are we starting with? So we call that initial value. Okay, our B here, this is kind of like the 3 in our previous example. So you'll see words like doubling, tripling. This is going to be the growth rate, basically. And tomorrow we're going to do decay, so I'll also say decay rate. Okay, so an example would be like doubling, tripling, etc. Okay, y is going to be our future value. So out of the equation that we created above, we find the future value of bacteria cells by plugging in values into our equation. So this will be future value.
So, sorry, what would you plug into y as the future value?
So we're not plugging in anything for y, but if I want to find the population on day 15, let's say, I'm putting 15 in for x, and then once I calculate over here, I'll get the number, the future number of bacteria cells out.
Like the result?
The result, yep. Okay, future value, and then x has 2 components to it. So x is anything to do with time. So if you see anything with time, it's going to be total time. So how much time has passed since the beginning? And this is going to be the growth or decay period underneath here. Pardon?
1 divided by, right?
Divided by, yes. Total time over growth or decay period. Just as a little hint, the growth or decay period is usually always going to come right after the growth or decay rate. So we'll be saying something like doubling every day or tripling every 2 days or whatever it is. So in our question here, it says it triples in number every day. 1 day is technically the growth period for this example. Okay, so we had like technically total time over 1 here, so that's why we were allowed to just put in just x, because it was kind of like over 1. George, question?
If it triples every 2 days, that would be 2 days or what?
It would be 2 days. So you would have 3 as your b value, and then when you enter in for times, if I wanted to know after 10 days what would happen, I'd have to divide that by 2. because it's tripled 5 times in 10 days if it triples every 2 days. Does that make sense? So x is basically like the number of growths or decays that have happened in your total time period. Okay? Okay, so if my population, let's just say, is doubling every 5 days, how many times would my population have doubled after 20 days? 4 times. That's x. So we would do 20 divided by 5, and it would tell me that my population has doubled 4 times within that 20-day period. Okay. X is the exponent, yeah. So this is b to the exponent x. All right, so let's take a look at another example here. Your brother tells you a secret. You see no harm in telling 2 friends. Be honest, who's ever done this before? You say like, okay, I know this secret, but don't tell anybody, okay? Like, this person told me, but you're not allowed to tell anybody. Guess what that person's gonna do? You just told that person, they're gonna tell somebody else too. Okay, so this is how rumors spread, right, guys? So your brother, he's gonna tell you a secret, and then you're gonna tell 2 friends. And then guess what those 2 friends are going to do? Even though you say, you can't tell a living soul. They're going to go and they're going to tell people too.
Unless it's your brother.
But your brother told you.
But I tell people about my brother's secrets.
So you're making the argument it doesn't matter. Because you're your brother.
Because the secrets are like really lame or like not even like secrets.
All right. Okay, so here's the idea. You're telling 2 friends, and those 2 friends, they're also going to tell 2 people. So now, after those 4 people knew, now your 2 friends, they tell 2 more people. Now 8 people know. You, your brother, your 2 friends, and also their 2 friends each. Okay, so if each of these friends continues to tell 2 people, then we're going to have, like I said, 8 people, and then 16 people from there. And if this pattern of spreading continues, how many people will know the secret after 10 such passings? Okay, so this is actually a totaling question, right? So how many people first initially know the secret? 1 person, your brother knows. Okay, and then he tells you. Now how many people total know? 2 people. And then you tell 2 friends. Now how many people know? And then they tell 2 friends. How many people know? 8. And so on. We can continue the pattern, right? So if those 4 friends that our friends just told now tell 2 friends, now a total of 16 people know, and so on, right? So we can kind of assume that this is going to keep happening, okay? And remember, this represents the total number of people that know. So if we were using our formula here, if we think about y, a, b, and x.
Well, basically the whole school knows it by day 10.
Basically, yeah.
That's quite unfortunate.
Okay, so y is the future value. This is going to be the total number of people that know. We don't know that at this point. That's the unknown, right? That's what we're trying to figure out. What is a? What's the initial amount of people that know? A is 1. Good. And what is happening after each passing of the secret? What are we doing to get from the total number of people each time? We're multiplying by 2. That's the b value. That's the growth factor. Zach?
The answer's 2.
What? Yes. B is 2, yes. Okay, x is essentially just going to be the number of passings. So every single passing, every 1 passing, there's going to be double the amount of people that know the next time. So this would be technically like total time that has passed or total number of passings over 1, because each passing, the total number of people are growing by a factor of 2. So x here really is just equal to t. Okay, or you can just leave x as x for this one.
T over 1, sorry.
So this is every 1 passing. After each 1 single passing of the secret, or like at each level, it's doubling the amount of people that know.
Is it 10 then?
What? So we're going to put that in for the total number of passings, yes. So when we sub into our formula, what we're interested in is what is the future total of people that know after 10 passings of the secret. So that's going to be 2 to the exponent 10, 10 passings. Pardon? I'm just showing you the plugging into the formula, but no, you don't really. Okay, so how many people know after 10 passings of the secret? Zach? Total of 512 people know.
We have around 700 in school.
We have like 675. Yeah.
It feels like it's like 400.
Okay, what's the moral of this story?
Don't be a snitch.
Don't be a snitch. That's exactly it. Good job, Sheila.
I got you.
Sheila, we all know your darkest secret. Like,
Actually, we
your
don't.
darkest secret.
She wouldn't be done with all
Ooh.
I'm gonna do my math now.
She looked at Josh and she was like, at least I'm not a goalie.
All right, so the takeaway here is if you're going to tell your secret to somebody, make sure it's someone that's trustworthy. And if you're being told a secret, make sure that you keep that secret to yourself, because then if you pass it to people, then all of a sudden after 10 days, like 500 people know. Okay, so a couple elements, guys, that I just want to point out to you here. A great idea is to start by identifying each of your variables here. Zach, shh. Identify your variables, plug them into your formula. You're going to come out with an answer, and then you are going to interpret that answer. This therefore sentence is your interpretation of your answer. So it's great to be able to do the math. It's even better to be able to interpret what it is that the math is telling you, right? So you need to create a final therefore statement for all of these questions, okay? All right, let's try another one. An insect colony has a current population of 30 insects. Its population, I'm just going to wait till everyone's ready here so I'm not talking over people. Okay, its population doubles every 3 days. What is the population after 12 days? Okay, so anything to do with time, it's controlled by the other room. Anything to do with time has to do with x. All right, so current population of 50 insects. Let's just write out, we have y, a, b, and x. What do we know out of all of these pieces of information here? Can someone answer what's one variable that we can fill in? Charlie? A is equal to 50. This is the initial population of insects. That's how much we start with. What else? Ethan? B is equal to 2. It's a doubling population.
X is 4.
X is 4. How did you get that, Lauren?
I just spotted 3 right here.
when 12 by 3.
12 by 3?
12 by 3, yes. So total time, our total time is going to be 12 days have passed. And the doubling period, it doubles every 3 days. So this is going to be 12 over 3. So in those 12 days, the population has doubled 4 times. That's why X is 4. Okay, so let's plug into our formula. Why is the question mark here? So guys, bed mass.
Goodness.
What do I do first? The exponent of 4 or the 50 times 2? Exponents first. So we're calculating 2 times 4 and then multiplying that by 50. I do not want to see 100 to the exponent 4 on the next line. Okay? That is a bed mass violation right there.
Brackets then exponents?
Yes, but those aren't.
Well, these brackets, we would have to simplify inside a bracket, but the brackets represent multiplication here. Okay, so as far as bed mass here, we're calculating 2 to the exponent 4, which gives us 16, and then you can multiply it by 50. Okay? If you do this in your calculator should take care of it for you. So you should get 800 here. Okay, can someone make a final statement for me here? Therefore, Lauren?
If we're after 12 days, the population is 807.
Great.
It's an insect. I didn't say insect. Open your ears. It's not hitting.
What? The one we just did?
Great. So again, a couple things that you're seeing here. I'm identifying y, a, b, and x. I'm showing the substitution into the formula. I am calculating. I don't need to see this step, but calculate it. And then I'm giving a final sentence which interprets that answer. Okay? So far, so good. Any questions on this guy? No? Okay. All right, so I'm going to introduce to you guys a little something that helps us isolate for variables, because you'll notice in some of these questions, if I have to isolate for the exponent, we've actually never really done something like that before in math. So we're going to introduce it to you. So there is a way that you can do this without the log function, but if your answer is a decimal, it becomes increasingly hard to guess and check. So for instance, what I mean is 3 to some exponent x equals 27. We could probably grab our calculators here and we could try a couple different exponents on 3, right? We know 3 to the 2 is 9. 3 to the 1, that's just 3. And then if we tried 3 to the 3, that's going to give us 27. So here we can assume x equals 3. Okay, so I know because, with guess and check, because 3 to the exponent 3 equals 27, therefore x must be equal to 3. Okay? I'm writing this off to the side because I want to show you the way that we use a function called log in order to isolate for an exponent. And this alleviates the idea of guess and check. Okay, Zach?
How you do that in calculator?
This one, this right here,
Oh, you said okay. Yeah.
this would be just guess and check. So I would be trying different exponents on 3 in my calculator. Okay, I'll wait till everyone's back with us here. Pardon? Okay, so suppose it was very difficult to guess and check. Maybe I have a decimal, that's my answer here, right? It's not always going to work out to be a perfect number. So here's what we do. There's a little function on our calculator, but we're not going to touch it yet. But I am going to take what is called the log of both sides of my equation. So we know whatever we do to one side of an equation, we also have to do to the other. Okay? And the most you need to know for right now, we're going to unpack logarithms in our next course. So if you decide to take advanced functions, you'll learn a lot more about logarithms. But for our purposes right now, log helps us isolate for a variable in an exponent. Okay, and what you also need to know is that log is a function. So log is going to actually take our number in and perform an operation on it just like a square root does, or a squared. So a square root, if I square root something, it's going to perform an operation and then it's going to spit out a value, right? Just like any other function or operation does. Okay, so when we do log, the cool thing about logarithms is that they're kind of related to exponents in the sense that some of our exponent rules come into play. You don't have to worry too much about that. But when I have the log of something to an exponent, the log actually allows me to take the exponent and bring it down in front and write it as a multiple of the logarithm, okay? So you don't need to understand the why behind this at this point, but basically what I'm allowed to do now that I have a log in front is write it as x times the log of 3. Okay, we call this power rule. I also like to call it parachute rule because we kind of like bring the x down and we parachute it in front. Okay, so now, right now, this is x times the log of 3. How do I get rid of a multiple of the log of 3? I will, what's the opposite? I will divide. So we'll divide by the log of 3 to get x by itself. And now I want you to look at your calculator. Everyone is going to have a log button. And we're just looking, some of you guys, if you have this calculator that has the blue and orange on it, you have two buttons. You have a regular log button, and you also have a button that's like right over here. That is the log, and it has two boxes. I want you to use this button. Okay, everyone find a log button on their calculator. Okay?
I don't have one of those.
You do.
Not the one with the...
Okay, you do your test. You're not involved in this right now. Is anyone having any trouble?
Will this be the answer?
So your log button's right
Really
there.
weird like this.
So you have to close your bracket there,
That doesn't make a difference.
doesn't it?
I have log, but like, so I just
Yeah.
plug in.
So you're gonna plug in opposite. So you'll do like 27, and then you can hit log.
Remember negative log in chemistry?
Yeah.
Wait, so what do I do? So I have the button.
So you're gonna use.
It's kind of the opposite of this.
Okay. I guess you're gonna just use the. Okay. Hey, wait. Where did you get that one?
Wait, what? It was shift and then it was this one.
Oh, perfect. Okay. So then you can do 27, and then divide by log 3. Don't use the other button. Yep.
In chemistry, we do like negative log by pH.
Yes, so we're actually, in advanced functions, we unpack like why you use logarithms, but basically it comes from the fact that logarithms are connected to exponentials, and like when you talk about pH, something that has a pH of 7, let's say, it has 10 to the negative 7 moles per liter of hydronium ions, right? So that's where we can actually use log to help us isolate for those pH values because they're exponents. Yep. Sweet. Okay, so did everybody try this out on their calculator? You did log of 27. It will probably open a little bracket for you. You close the bracket, and you should get 3 out here. Shh. Okay, and that's because 3 to the exponent 3 equals 27. So the log function can help us find exponents if we don't know them if they're unknown in an exponent. Okay, so it'll help us isolate for the exponent. Okay, so if we tried to guess and check with this one, it would be probably pretty difficult for us to find exactly what x is equal to, because 4 to the exponent 2 is 16, and then 4 to the exponent 3 is 64. So I know it's probably somewhere in between there. Yeah, so then, and then I'm even getting into like, is it 2.123? Like, I don't know, right? So the log can help us in situations like this. George, do you have a question?
What do we use the log button for?
So the log button, basically, the big thing is that log helps us get the exponent out and down in front as a multiple.
When I press log on my calculator,
Yes.
it just gives me a bunch of numbers.
Yeah, so you don't have to worry. For our purposes right now, log is helping us isolate for an exponent. That's basically all you need to know for now. Okay? All right, so we're going to try this guy out here, see if we can use log. So first thing, we take the log of both sides. So whatever I do to one side, I must also do to the other. And the log function allows me to take any exponent on a logarithm and parachute it down in front as a multiple.
What decimal place do you want us to go to?
Let's go to 3 for this one.
3. Okay.
Okay, and now how do I get x by itself?
You divide by log 4.
We will divide by log 4, that's right. Okay, so in your calculator, you're going to enter in log of 35 divided by log 4. If you're having any difficulty getting your answer, I will touch base with you after, okay? Zach, what'd you get?
If you write down 4 log or log 4.
It does matter, yes.
That's how you don't put
That would be like me writing down 4 root instead of the square root of 4,
Sorry, how many?
right? So it needs to be inside the logarithm.
How many decimals?
Let's go to 3 decimal places here, guys. What did you get?
2.564.
I think it would round up to 5 here, right? Because it's 2.5646.
Mine didn't come up with extra.
No? It only came up with 3?
It only came up with 2.56. It just said 2.56.
Might be the setting on your calculator. I'll check that out for you. Okay, so if you guys do a little check, shh, Zach. I don't want to hear your voice for the rest of this lesson, okay? Zip it. Okay, let's do a little check. If you enter into your calculator,
4 to the power of answer is 30.
you should get approximately 35. Now, because we rounded this a little bit, when I enter in 2.656, or it's 565, sorry, I'm getting like 35.017, and that's, again, due to rounding. So we get very, very, very close, approximately equal to 35. That's why the more decimals we keep, the stronger that answer is going to be, right? So at least I would say you would keep 3 decimal places, if not more, if you're using that for a future calculation. Okay? All right, so when we see an unknown in an exponent and we have to solve for it, we want to think log, okay? All right, so there's a part B to our question from above. So we had an insect colony. It had 50 insects. It was doubling every 3 days, okay? Now, plot twist, the insect colony is actually full of giant, intelligent, mutant insects. They plot that they can overtake the Earth when their population, sorry, I have this typo every year and I forget to fix it. When their population has reached 1 billion. When will we meet our doom? Or in other words, when does the population reach 1 billion? I know. They're giant, okay?
Bigger than you, Sheila.
Goliath is shaking, quaking.
Okay, so how many insects did we start with in part A? What was our initial population? Okay, we started with 50. It's still the same. What's happening to the population? What's the growth factor? It was doubling, right? And I don't know when the population will reach 1 billion, so I'm not quite sure exactly what the total time will be, but I do know how long it takes to double. How long does it take to double?
12 days. No, 3 days.
It took 3 days, yes. And why for this? This is our future value. Yes, Zach?
Can we just go off the story you read us for us to get this?
No.
Because like it'd be around 93 days.
So, yeah, so we could probably like approximate it, but we want exactly, precisely. Okay, so I'm curious when this insect population is going to reach 1 billion. That's 1 with 9 zeros, 1 billion, that's the future value. So we want to know how much time that's going to take. That's what we're trying to find, time. That's the unknown. Okay, so we're going to sub this into our formula. And also, Zach, this question is a little bit different than our scenario because she was doubling her grains of rice every day.
Yeah, that's why.
We're doubling every 3 days. Yeah.
Instead of 30-ish days.
Okay, so guys, really important part about logarithms. Before you take the log of both sides, you need to have the base and the exponent that you're trying to find alone on one side. So I need to remove this 50 from this side. How do I get rid of a multiple of 50? We divide by 50.
So why do you want to get rid of 50?
So I can't take the log until I have the base and the exponent isolated on one side. Okay? So what's left here? We have 20 million? Yes. So 7 zeros here.
It's 20,000.
I think it's 20 million because this cancels and then,
More than 7 zeros are there?
what? 20 million?
Huh? Wait,
Oh, it's a billion. Oh my gosh.
you said 700 zeros?
Wait, no, I didn't say that. I forgot it was a billion. That doesn't. Never mind. You know
That's
what?
okay.
I'm just.
No worries. Okay, so now we have something that's somewhat in this form. We have something to an exponent that we don't know is equal to something else. So when you get to this point, the base and the exponent are isolated. Then you can take the log of both sides. And this is only being used, we're only using log if we have an unknown and it's in the exponent. Otherwise, I don't have to use log, okay? So only if your unknown is up here or here. Okay, so we're going to log both sides here. Do not plug this into your calculator yet, okay? You should be fully isolating for t, and then right at the end you can sub it into your calculator. Okay, so with the log, now that we have the log in front of some base to an exponent, we will bring down this exponent. This is called power rule of logarithms, and we can write it as a multiple in front of our log. So we'll have t over 3 times the log of 2. Yes, so now I want to start moving things away from t. So we're going to start, if this is multiplication right now, we're going to start by dividing the log of 2 on each side. And you may be tempted to plug into your calculator at this point, but just wait 1 second. No, Zach's not interested. So I have t divided by 3 left now. How do I get rid of division by 3? Yeah, let's multiply by 3. So I'm going to multiply that up on both sides. These sides will cancel, and I'm left with t by itself. So we're going to enter into our calculator 3 times the log of 20 million, see what that's equal to, and then divide it all by the log of 2.
Wow.
That was way off.
Is it exactly 72?
72.76.
Okay, 72.76. What's the unit of measurement for time here? So if we entered in the growth period in days, we will get out an answer in days. If I enter in the growth period in seconds, I'll get out an answer in seconds. So this is going to be days. So we will meet our doom in 72 3/4 of a day.
As long as before exam.
Or we'll need to be ready with heavy artillery by then. We need to have a plan. At least by 72 days,
We
right?
have like
How
3
many
handguns
days
on
away is
each
the
other.
growth period?
It's a little over, it's like about 2 months and 2 weeks
Oh, I can
ish.
May. I'm saying May.
I wonder if that's Hello Kitty hand grips.
Like, seriously.
Do we have to write to that first statement?
Yes, always.
How old days?
Okay, if we want to be fully prepared, we should be at least ready by about day 70 to start fighting the giant mutant intelligent insects off.
I said May 20.
As long as
May
the-
21.
Nice.
Oh, May? First?
Lauren and I will get our birthdays in before that time, so it's all good, right?
So alive, we're chilling.
All right. Just as a little note, guys, 2 more seconds of your attention, more like a minute. So in some of your questions, you might see growth by a percent, okay? So let's just say, for example, it tells you that your population grows by 7% per day. The growth rate is indeed 7%, but I can't enter in percents as the B value. And I also need to consider that if I'm growing by 7%, it actually means I have 100% of what I already have, plus an extra 7%. Agreed? So if a population, let's say, or an amount of something is growing by 7%, I have 100% of what's there already, plus an additional 7% growth. So this actually is really like 107%. Now when you enter this in for B, you need to enter in the percentage as a decimal. So how would I express 107% as a decimal? Percent is out of 100, right? So if I take 107 and I divide it by 100, I get 1.07, or move the decimal left twice. This is what you would enter in for B if you're talking about percent growth. Okay? So 100 plus the percent, you'll get 107% or whatever it is, and then you need to express the percent as a decimal. Cool? Okay. This is just a little kind of summary of what we did. And then we're going to try some questions today.